Welcome to week 12 lesson. We're going to go ahead and get started with quadrilaterals. All right, so quadrilaterals, basically anything with four sides. Any shape with four sides is going to be a quadrilateral. So any shape with four sides. We have a lot of examples, right? We know rectangles and squares, right? Remember those both have 90-degree angles. We've got parallelograms. Of course, those are just like a rectangle that's sort of tilted over on its side. And then if we allow all the sides to be the same in that parallelogram, we call it a rhombus. And then trapezoid. That's like basically it's like a triangle where you chop its head off and it allows you just to have this parallel sides on top and bottom with these two legs that we call. So that's trapezoid. Remember, rhombus, basically a parallelogram with four equal sides. Parallelogram, of course, is like a rectangle. It's been tilted on its side. Square, all four sides are the same. Rectangle, we all know about those. So anyway, all right, let's focus in first on squares and rhombuses. All right, so what's the deal with squares and rhombuses? Well, first of all, I'll give you a little bit better of a picture here. All right, we've got four 90-degree angles and four equal sides. This, of course, is going to be our square. And then very similar to that, although just not the 90-degree angle piece. So if I have those same four equal sides, and now I tilt it over a little bit, that's what we're going to call a rhombus, okay? Just like a square. So squares and rhombuses kind of have a lot of stuff in common. So here's some things to note. Here's what we know about the sides of these shapes. These two shapes, here's all the information about the sides. First of all, there's four equal sides. All the sides are the same length in a square and a rhombus, okay? Now, opposite sides are going to be equal to each other. So opposite sides are equal. I'm using that equal sign there to show that. So four equal sides, and of course, in addition, opposite sides are equal. So you know that opposite sides are equal, and in fact, all four are equal. Now, what do we know about the angles of a square and a rhombus? Well, the opposite angles, and I'm going to use this symbol there for angles, right? That's the angle symbol that I'm going to use. Opposite angles are equal to each other. So what do I mean by that? Well, when I look at this picture, I'm saying this angle and this angle, those are opposite angles. They're on the opposite side of the shape. Those two angles are going to be the same. Also, this angle here and this angle here, those are opposite angles. Those are going to be the same. Now, of course, when you're looking at a square, the opposite angles are going to be equal. But really, even more than that, all four of the angles are going to be equal. But we still say that opposite angles are equal. Okay. Also, we know that adjacent angles are supplementary. So adjacent angles are supplementary. Now remember, what supplementary means is that they add to be 180 degrees. So what I'm saying here is if I look at this angle and this angle, those are adjacent. They're like next door neighbors. Those two angles add to be 180 degrees, okay? Or if I look at these two angles, this one and this one, those are adjacent angles. They add to be 180 degrees, okay? This one's really, really important. It's one that pops up all the time, and it's one of those things you just have to know. Otherwise, you won't get that kind of question right. Okay, so next, what about the diagonals? Okay, now remember, the diagonals are the lines that connect the opposite angles together. So there's one diagonal. Here's another diagonal, okay? I'll do one on the square as well. Here's a diagonal on the square, and here's another diagonal on the square. Those are my diagonals. They're from corner to corner, okay? So what do we know about diagonals? We know that the diagonals bisect each other. Okay, so let's say I have a parallelogram, or excuse me, a rhombus, and I've got this diagonal and this diagonal here. Well, I know that this diagonal cuts this one into equal parts. And that's why I'm going to notate that with those little lines. That means they're the same length. Also, this one is going to bisect this one. So these are the same as well. So I'll put 2 marks to show that they can be different. But when those diagonals cross, they cut the other diagonal in half. So that means that I can say that this diagonal is equal to this diagonal. I can say that in this situation. Also, the diagonals are perpendicular to each other. So not only do they bisect each other, but they bisect at right angles. Okay, so I've got this, you know, it's easy to see with a square that there's going to be a right angle there with those diagonals. But with a rhombus, it's a little more difficult to see, but here's my diagonals. I have to realize that those cross at 90-degree angles, okay? Again, that's really, really important. These 2 things for sure are very important, along with the angles being adjacent angle supplementary. Those are the 3 big ones you've got to really remember here, because they're going to ask questions like that on the test. Okay, finally, there's some differences, okay? There's some things that are different between these 2. So what are the differences between rhombuses and squares? So between rhombus and a square, what are the differences? Well, a square has all 90-degree angles, which means because those angles are 90 degrees, it means that those diagonals are equal. They're congruent. The diagonals are the same length. You can see in this rhombus, right? If I'm looking at this picture up here in the corner, this rhombus picture, that blue diagonal is longer than the yellow diagonal. They're not the same length, okay? Whereas in the square, if I'm looking at this square picture here, I can see the green and the blue. Those are exactly the same. So that's the difference there, is that the square has 90-degree angles, therefore those diagonals are going to be the same length, okay? You'll see that pop up with some other shapes as well. That usually is the case. Okay, so moving on to the next set, rectangles and parallelograms. Okay, so first off, here's an example of a rectangle. It's got those 90-degree angles that we're used to. And then we've got these opposite sides that are equal. So what does a parallelogram look like? Looks like a rectangle that got tilted on its side. So these are still the same, and these are the same. Of course, remember these opposite sides are parallel. We know that for sure. Okay, so let's see. What do we know about the sides? We'll start with the sides. Okay, we know that the opposite sides are going to be equal to each other. Okay, those sides that are across from each other are going to be equal in length. We also know that the opposite sides are parallel to each other. Okay, so we know opposite sides are equal and opposite sides are parallel to each other. All right, what do we know about the angles in both a rectangle and a parallelogram? Well, we know that opposite angles are going to be equal here, right? If I look at the blue angle here, it should be the same as this blue angle here. Those opposite angles are going to be equal to each other. And actually, I can tell right now that you're not going to be able to see that drawing. So let me cross this thing out and redraw it down here where you might be able to see it. All right, so we've got these opposite sides that are parallel and equal. And what I'm saying is, is that this green angle and this green angle are congruent. Those opposite angles are congruent. I also can tell that this angle and this angle are going to be congruent, okay? Because it's a parallelogram or a rectangle, I know that information, okay? We also know that adjacent angles, so neighboring angles, angles that are right next to each other, adjacent angles are supplementary, so they add to be 180 degrees. Okay, we know that about the rectangles and parallelograms. All right, so moving on to the diagonals. What do we know about the diagonals? Well, they bisect each other. Okay, we know that when they cross, when I look at these diagonals here, I've got a diagonal here and a diagonal here. They bisect each other into equal parts. Well, I know that those diagonals bisect each other into 2 equal parts. Okay. Now, they are not perpendicular. And that's the symbol for perpendicular there. They're not perpendicular, okay? And it has to do with the fact that all four sides are not the same, okay? That's why they're not perpendicular to each other. All right, so what are the differences between the two shapes? Okay, well, rectangle has 90-degree angles. Has four 90-degree angles. So what does that tell us then? Do you remember this from when we talked about squares and rhombuses? Yeah, it means that the diagonals are equal in length. So the diagonals are the same length as each other, okay? And that has to all do with the rectangle having those four 90-degree angles. So the rectangle, again, has equal diagonals, but not the parallelogram. So yeah, it's the fact that those four right angles make those diagonals equal to each other. Okay, so one thing right here is that you are going to have to be able to do this on the test. You're going to have to prove that a shape is a square or a rhombus or a rectangle or something like that. They're going to give you like basically coordinates on a coordinate plane, and they're going to ask you to say, is this a square? Is this a rectangle? Is this a parallelogram or a rhombus? Okay, so you're going to have to prove that a shape is maybe a square or a rhombus, right, or a rectangle, or a parallelogram, right, the parallelo. Okay, the way you're going to do that is by slope and by distance. So you're going to use the slope formula, which if you remember is the difference in the two y numbers divided by the difference in the two x numbers. Okay, that's my slope formula. And then of course my distance formula is the distance in the two x numbers squared plus the difference in the two y numbers squared, and then all that added and then square rooted. It's just Pythagorean theorem in disguise. But what you're saying is like, okay, we know that a rhombus has four equal sides. So you'd have to use four distance formulas to prove that all four of those are the same. Then you would want to look at the slope, and we're gonna see this later too, that if two lines have the same slope, then they're parallel to each other. So then you would show that these two lines have the same slope. I'll color code them here. You'd show that the two green lines have the same slope and the two red lines have the same slope. That's how you would do that. And alternately, to show a right angle, right, you're going to know that the slope here, let's say the slope here is 2, then the slope here would have to be -1/2. It has to be that negative reciprocal. And again, we're going to go over that in a later class, but just be aware that you're going to have to prove all these shapes. So when you're thinking about all these properties that these shapes have, you want to also be thinking, oh yeah, I would have to use this information to prove that a shape was a rhombus, okay? Or to prove that it was a square. All right, so moving on. Our next topic is going to be polygons. So basically any figure with 3 or more sides is a polygon, okay? There's some basic fundamental ideas that you have to kind of memorize here. When I say interior angle, okay, I'm talking about these ones on the inside. These are called interior angles. So you'll see that that's what I'm talking about when I say interior. Now, if I were to extend this line out, now I've got what I call an exterior angle. So these are the definitions of interior angle and exterior angle. So exterior is basically 180 minus the interior. So when I talk about those, that's what I'm talking about. So the first property, the sum of the interior angles of a polygon. Okay, so we've got polygon, 3 or more sides. The sum of these interior angles, if I want to add up the measurements of all these 5 interior angles, what am I going to get? Okay, well, let's think about a triangle. Okay, we know that the sum of a triangle is 180 degrees. Okay, so if it has 3 sides, the sum of the interior angles is going to be 180. Okay, let's think about like a rectangle. We know that all 4 of those are 90, so 90 plus 90 plus 90 plus 90, that's 360. Okay, now it's funny, but you know, if you make a parallelogram, it actually has the same, it has to do with these 2 angles add to 180 because they're supplementary, right? We said adjacent angles are supplementary, so that makes 180 and that makes 180. So either way, these 2 make 360 degrees total. So four-sided figures always sum to be 360 degrees. So the question is, what if like it's 12 sides? I mean, what's the sum of the interior angle of a 12-sided polygon? Or a hexagon, right? I mean, a hexagon is a 6-sided polygon. Well, let's find out. So what you want to do is you want to think about this rectangle here. I'm going to think about this rectangle here. What I'm going to do is I'm going to cut it down the middle, okay? How many triangles do I have there? Looks like I have 2, okay? Let's go up to this shape, actually, this 5-sided figure, and let's take one of the vertices, right? We'll start with right here. We're going to connect it to the other sides there. That makes 3 triangles, okay? So the deal is, we know each of these triangles has 180 degrees. So 180, 180, and 180. If I add those together, I get 540. So if I kind of make a table here, the number of sides and the sum of the interior angles, okay? If I have 3 sides, it's a triangle. We know that it's summed to be 180 degrees. 4 sides, like a rectangle, we just saw that it was 360. And 5 sides, it was 540 degrees. The question is, what if it's just n? So any number, can we come up with a formula that figures this out? Well, yeah. It has to do with the number of triangles that you can create within a shape, right? If I look at my 5-sided figure, I made 3 triangles. That's 2 less than the number of sides, right? 5 sides, 3 triangles. That's 2 less. Think about my rectangle here, right? 4 sides, I made 2 triangles. That's 2 less, okay? There's kind of a pattern developing here. Looking at my triangle, 3 sides, 2 less would be 1. There's only 1 triangle that I can make on the inside of that triangle. So that sort of makes sense. So really what we do is we do n minus 2. Whatever the number of sides is, we take away 2, and then we realize that each of those triangles that we just created, right, is going to have 180 degrees in them. So we do n minus 2 times 180. So that is the formula, basically, n minus 2 times 180. The formula for the number, or excuse me, for the sum of the interior angles of a polygon with n sides. Okay, so if we say it has n sides, then we know the formula is going to equal n minus 2 times 180. Okay, that's going to be the total interior angle sum of any polygon with n sides. So let's look at an example, right? The kind of questions they'll ask is they'll say a 14-gon, which is really a 14-sided polygon, right? What's the sum of the interior angles there? Well, we use our formula, n minus 2. Well, n is 14 because n is the number of sides. So we do 14 minus 2, and whatever that is, we do times 180, okay? That's pretty easy. I just get out my calculator. I do 14 minus 2, that's 12, times 180. That's going to give me 2,160. So the sum of the interior measures of a 14-gon is 2160. Okay? That's the kind of questions they're going to ask. Now, alternately, they could say, what if the sum of a polygon, the sum of the interior angles was 1,800 degrees? Find the number of sides. So basically, they're asking it backwards. So remember, our formula is the sum equals n minus 2 times 180. So we're just going to use the opposite of that. We're going to say the sum was 1,800. The sum equals n minus 2 times 180. And then we just solve for n. So I can divide by 180. That's going to get rid of that 180, first of all. Got to do it on both sides. That cancels there. It leaves me with 10, right? 1,800 divided by 180 is 10. So I get 10 equals n minus 2. Then I just add 2 to both sides. I get 12. So that means the sum of the interior angles was 1,800. It came from a 12-sided polygon. So you can use that formula in both directions, okay? All right. So on to what we call regular polygons. Okay, these are special kinds of polygons. Basically, they have equal side lengths. Okay, all the sides are the same, and all the interior angles are equal as well. So obviously with a triangle, with all the sides the same and all the angles equal, we call that an equilateral triangle. When it's four-sided and all the angles are the same and all the side lengths are the same, we call it a square. But anything after that, like a six-sided shape, that's really amazingly beautiful. But just imagine all these sides are the same and all these interior angles are the same. We would call that a regular hexagon. Okay, six sides, that's a hexagon. If all the angles are the same, all the sides are the same, we call it a regular hexagon. So it's kind of got its own formulas here. So these regular polygons have the same formulas. So first of all, the sum of the interior angles works with regular polygons just like it does with what we just learned. And it's actually the same formula. So the sum is n minus 2 times 180. So we don't change that formula at all. That says n minus 2 times 180. I know it's kind of stuck behind my face. So same for when we deal with all polygons. But we kind of can add to that. So each interior angle, so what is just one of the interior angles, okay? Basically, what we do is we do n minus 2 times 180. We do that same formula, but then we divide it evenly amongst the n sides. That gives us what it would be. So like in a triangle, right? We know it's 60, but let's calculate it using the formula. 3 minus 2, because there's 3 sides, so 3 minus 2 times 180. That's going to equal 1 times 180, that's 180. Then we divide by n, the number of sides. We divide it evenly by 3, that gives me 60 degrees. So each of these angles here is 60 degrees, right? Using the formula. Think about it with a square, right? Well, the formula would say 4 sides, so 4 minus 2 times 180 divided by 4. Well, that's just 2 times, that's 360, the total sum, divided by 4, we get 90 per side. Okay, that works for any side. I'm just showing you the ones that you kind of knew already, just showing you how the formula works. So that's when you want to know just one interior angle, you do that. Okay, so what if you want to know one exterior angle? Okay, and I remember we just briefly talked about it, but just to remind you, right, if here's a regular polygon, you've got this extension. This angle here is our exterior angle. Okay, remember, it's got to come from a regular polygon. If it's not regular, that means all the angles aren't the same. We're not going to be able to accurately predict the exterior. But what we could do is this. We could find the interior angle, okay? We could find the measure of one of the interior angles, okay? And then once we found an interior angle, we could do 180 minus the interior angle. That would give us the exterior angle. So if we knew this was 60, we'd do 180 minus 60, that'd be 120. Okay, that's one way you could do it. There is actually a shortcut though. Okay, so this is the second way that you could use, that you could find one exterior angle. It's just 360 divided by n. 360 divided by the number of sides is n. Okay, so what that means is in this triangle case, I do 360 divided by 3, it gives me 120. Notice how that's 120. So it's a little bit faster, okay? Now, one thing they could ask you is what is the sum of the exterior angles of a polygon? Okay, well, basically, if each exterior angle is 360 over n, that's each one. And how many of those exterior angles do we have? Well, in our triangle example, you can see we've got 1, 2, 3 exterior angles, okay? Well, we multiply by n, and what happens is the n's cancel, and you actually get 360. So no matter what the polygon is, the sum of the exterior angles is always going to equal 360 degrees. Okay, that's one of those things you just kind of got to know. All right, so let's look at an example of this. Let's say we have a 10-sided figure, so a decagon. Okay, I want to know all these things: the sum of the interior angles. I want to know the sum of the exterior angles. I want to know each, let's say this is a regular decagon, sorry. I want to know each interior angle, and I want to know each exterior angle. Okay, so let's just find these real quick. So we know that n is equal to 10, so we're just going to use our formulas. The sum of the interior is going to be n minus 2 times 180. Okay, so 8 times 180, that's going to be 1440. Excuse me, yeah, 1440. Okay, that's the answer to this first question, 1440 degrees. Some of the exteriors, remember that's always 360. That's our easiest one. If they ask that question, we got that one. Each interior angle is the total of the interior angles divided by n, which n is 8 in this case. So I would get out my calculator here and do 1440 divided by 8 to see that each one is 180 degrees. Okay, I'm sorry, we're dividing by 10 because there's 10 sides, my bad. So 1440 divided by 10, of course, that's just going to move the decimal place over 1, so it gives us 144 degrees. So 144 degrees. That mistake happens all the time, actually. I mean, I make the mistake, obviously. It happens a lot. So just make sure you divide by n. We used 8 because it's n minus 2 is 8, but n is 10. So when you divide by n, you're dividing by 10. All right, and each exterior angle, remember that's going to be 360 divided by n. So each exterior angle is 36 degrees, which of course we knew from the interior being 144, right? If we're thinking about our interior was 144, our exterior here had to be 36. So if you already knew the sum of the interior angles and you found one interior angle by dividing by n, I would just take it away from 180. But that works as well. So there you go. That's our example. All right, so let's move on to the area of a a regular polygon. Okay, how do we find the area of a rectangular polygon? Well, there's two options here. Okay, there's a really good shortcut, and we're going to talk about that second. But first, we'll talk about just what it looks like here. So let's say we have a regular hexagon. Okay, 6 sides, they're all the same, and all these angles are the same here. Okay, so we've got a regular hexagon. So what I'm going to do is actually find the center point, and I'm going to draw these little cross lines, these diagonals. Okay, what it does is divide it into triangles. So I know I could find the area of this triangle as an example. Okay, the area of a triangle is 1/2 base times height. Remember, the height is this horizontal distance there, that dashed line, and there's my base. So if I just found the base and the height, okay, then I could use that formula. All right, so let's say that we're looking at this triangle, and it says that this side here is 4, and this side here is 4. Okay, so all these sides are 4. That's what that means. And like, not the radius, because this, circles have radiuses, but if you think about this as a radius, that distance from the center to this corner point is 4 as well. Now remember, that's not the height of this triangle. If I kind of zoom in on this little piece of this triangle, we've got 4 and 4. What I want to know is the height here. Okay, now if you remember from last week, we've got these special triangles. If the whole thing is 4, that means this piece is 2 and this piece is 2√3. Okay, that's our 30, 60, 90 right triangle. Now it doesn't always work out like that, but because it's a hexagon, I know that this is actually 60 degrees, this angle here. So really, usually you should use Pythagorean theorem, but I know that's 60, that means half of it's 30. Since it's a right triangle, I know this is 60. With hexagons, it makes 30, 60, 90 right triangles. So I know that my area is 1/2 of the base, which is 4. Remember, the base is this entire distance, times the height, which is 2√3. That's the area of my little triangle here. So that's the area of this one little triangle. Then you just take that and multiply it by however many of those little triangles you have. Well, there's 6 of those. So I'm going to do 4√3 times 6, which is going to give me 24√3. It's a weird number, but that's really what the area of that shape is, that hexagon. That's the area of the hexagon. Okay. Now, alternately, right, this would have been a great time to recognize that this is 4 and 4 and 4. This is an equilateral triangle, right? I could have definitely used that formula that the area of an equilateral triangle is √3/4 times the side length squared. If I could have recognized that, it would have saved me some time. It would have been √3/4 times the side length of 4 squared, which comes out to be 4√3. Okay, that would have saved me a little bit of time. Then I could have found the total sum. Okay, so the second option here would be to use the formula. There is a formula for the area of a regular polygon. And let's go back to this hexagon shape. We're gonna calculate the same thing here. So first of all, what they call this vertical distance from the center to the middle of the nearest side, they call this the apothem. Okay, the apothem is that length, and they're going to use A for apothem. So in this formula, the area of this regular polygon is going to be 1/2 the apothem times the perimeter. So A is the apothem, which is that distance right here, and then P is going to be just the perimeter. So remember, in our last example, all of these side lengths were equal to 4 because it's a regular polygon. So there's 6 of them. That means the perimeter was 24. Now the apothem, again, we'd have to use this triangle, knowing that that length was 4, and then we have a 2. We could use Pythagorean theorem to realize that it's 2√3. And then once we have those two values, we just plug it into the formula. So 1/2 area times perimeter, the 2's cancel, and you're left with 24√3. So that's a quick shortcut. It doesn't save you a lot of time, but it is a little bit of a time saver, so it's worth mentioning. All right, moving on to the next topic. It's going to be similar shapes or similar figures, okay? Similar shapes. So remember, two shapes are similar. What it means to be similar is that they have the same shape, but different sides. Or different size, I should say. I mean, it does have to do with the side lengths. But if they have the same shape, but they're a different size, we say that they're similar to each other. So what makes something have the same shape? The same shape is basically defined by the angles. So shape means the angles are the same. Okay, different size means that the sides are different. So if the sides are not equal, we say they have different size. If the angles are the same, we say they have the same shape. Okay, now here's an example of two similar figures, right? That's a 90 and 45, 45, 90. So these two are the same. Those two leg angles, those base angles are equal, and that 90-degree angle is equal. So we say they're similar. A lot of the times we use a little curvy line like that to show similar. So we're saying that little triangle is similar to the bigger triangle. So here's what we know, okay? If two shapes are similar, okay? If I'm told that these two shapes are similar, what it means then is that all corresponding angles are equal. Now, corresponding angles just means like, I'm gonna go ahead and use some color coding here. If this angle here was 45, and it would be the same as this angle here, those angles are corresponding, they're in the same location. This little green one and this little green one are in the same position. Now remember, one could be flipped over. It doesn't have to be like the top is the top and the bottom is the bottom. It could be flipped over to where maybe instead of it being like that, maybe we've got the top one equals the bottom one, and maybe that the bottom one here equals the top one there. They don't have to be in the same orientation, but as long as all three angles in the triangle are equal to all three angles in the other triangle, then they're similar. And of course, this works for any shape. Could it be 4 sides, 5 sides, 10 sides, whatever. As long as the interior angles are all equal, then we say that it is a similar shape. Okay. All right, so again, what we said was that if two shapes are similar, then the corresponding angles are equal. And there's also something else here. The corresponding sides, right, those sides that correspond to each other are going to be proportional. All right, proportional. They're in the same proportion. If I look at the ratio between this big shaped side and the small shaped side, you're going to see that that number is the same throughout. Okay, so if two shapes are similar, corresponding angles are equal, and corresponding sides are proportional. Okay, all right. Then also, conversely, if corresponding angles are equal, right? Or if you've got corresponding sides proportional, then what do I know about those two figures? Then those two shapes are similar. So it works in both ways, okay? If you find out that the angles are all the same, you can say they're similar. If you're told they're similar, you can say that all the angles are the same, okay? It works in both directions. And the test will ask you actually both ways as well. So you got to know that. So let's look at an example, okay? So remember what we're saying is if they're similar, then the angles are equal. So as an example, are these two shapes similar? All right, what we've got is we've got a triangle here, DEF, and we said this is 60 and that's 73 degrees. And then we've got this other triangle here, it's ABC, and A is 60 and C is 47. Okay, so we don't know, are these two shapes similar? Well, it's a triangle with two known sides. I can find the third side. We just add up the two angles that we know. This one here adds to be 133 degrees if I add up 60 and 73. So that means there's only how much left for the third angle? Let's see, 133 would leave 47 degrees for this angle here. Okay, looking over at the other triangle, I've got 60 and 147. That makes 107 degrees total, which only leaves me 73 degrees for the third side. So that means this angle here has to be 73 degrees. And so because all these angles are the same, right? You got a 47, a 73, and a 60. We're going to say that these two shapes are in fact similar. So yes, I'm going to put that little squiggle to show that they're similar. So yes, they're similar. Now, when I say two things are similar, I immediately get a similarity statement. Okay, I can say that triangle ABC is similar to triangle DEF or FED or whatever, but does it matter which three letters I put here? It actually does. Okay, notice how angle A, if I say triangle ABC, if I start with A, I'm talking about the 60-degree measure. So I want to use the 60-degree measure when I write the equivalency statement. So I'm going to say F is first because that is our 60-degree angle. All right, next it says AB. So AB, we talked about A, we talked about B is 73 degrees. So which angle in the other triangle, in the DEF triangle, has an angle measure of 73? Yeah, it's E. So that means I'm going to put E next. Of course, that means I have to put D last. All right, so what this is saying, when you write this statement like this similarity statement, it means a lot of information, okay? This thing is packed full of info, and that the order matters here. Because if you put it out of order, you're going to be misleading yourself. What this says is that A and F are congruent. So angle A is equal to angle F. Now, technically, I should be using the word congruent. I'm just kind of being, you know, a little bit lazy there, but that's okay. And that means that angle B and angle E are congruent. So angle B, that would be the congruent symbol there, to angle E. And then finally, I know that the third letter and the third letter are going to be equal. I know that angle C is going to be congruent to angle D. Okay, I know that information. So that's, again, if the two things are similar, then I know information about the angles. And also, if I know the angles are the same, I can say they're similar. So that's how you would use that kind of idea to show similarity. Okay, and don't forget, this means something here very specific. When I write this ABC is similar to FED, I'm saying A and F and B and E and C and D are congruent to each other. Okay. All right. So if I have, let's see an example here. This is the kind of question they could ask. In quadrilateral, ABCD is similar to quadrilateral EFGH. So the question is, angle H is congruent to which angle? Well, it's the last one. The last ones are going to be congruent. So we would say angle D is the same measurement as angle H. Okay. So again, that's kind of a use of that information. That's how you would use that. Okay. So remember we said there's two things going on with similarity. It's the corresponding angles are congruent. Well, we also talked about proportional sides. So that's what we're going to talk about. Proportional side lengths. So remember, these are the corresponding sides are proportional to each other. Okay, so let's say we have this similarity statement. Triangle ABC is similar to triangle DEF. Of course, we know all about the angles, but let's talk about the side lengths here, okay? So first of all, the first two letters represent basically a side length, right? If I've got ABC here, and I've got DEF, okay? When I say AB, right, I'm talking about the length of this side. Well, it should be proportional to DE because that's the first two letters here, DE. Now, I'm not saying they're the same size. They're not the same size. These are actually different size. But I know the proportion of AB to DE, this ratio, this number over a number, this ratio, is going to be proportional, which means it's going to be equal, okay? It is going to be equal to the proportion of another pair. So we'll say BC this time, all right? And that's going to be EF. There's an F after that E. You can't see it. But that means that BC, the proportion of BC to EF, will equal the proportion of AB to DE. So those side lengths, the proportions are going to be the same. And so thirdly, I've got my AC and my DF. So side length AC over DF should equal those two things. That's what I'm saying when we say the side lengths are proportional. Okay, so let's look at an example. This can kind of get a little weird if you're, the way I write it like that looks a little strange. But let's look at an actual example. All right, let's say we've got a triangle with lengths 15 and 6 is similar to a smaller triangle with lengths 3 and some unknown length that I want to find out. Okay, so let's say this is A, B, C, and this is D, E, F. Okay, so what I want to be able to say is that if triangle ABC is similar to triangle DEF, I want to find X. Okay, well, first of all, we know AC. And AC is the first and last letter of that statement, so that means it should be paired up with the DF, which is that X. So I'm going to say 15 divided by X, the proportion of the larger triangle to the smaller triangle. The proportion of those corresponding sides should equal the proportion of the other side. So CB is right here, right? And CB is the last two, right? It's this BC or this CB right there. That should be the same as EF. So EF and the BC work. So 6 over 3. Now look, if you notice the top, it's big over small. So it's the larger triangle over the side length from the smaller triangle. Okay, got to keep it in that same order. If you accidentally flip it, it's not going to get you the right answer. So how do we deal with a fraction equal to a fraction? We always do the same thing. We cross multiply. Okay, boom, boom. So 15 times 3, that's 45, equals 6 times x, that's 6x, and then we just divide out. So we divide both sides by 6, and we get that x is equal to 7.5. Okay, so what that means is that this length here has to be 7.5. Okay, now one thing I want you to be aware is that you notice how the ratio from CV to FE was half. This should also be half. Sometimes you can look at this thing, this is called scale factor. The scale factor was 1/2 here. It's half as big. Or if you look at it the other way, we doubled. So you could say the scale factor was 2. But whatever that scale factor was, you can utilize that for your information, to your advantage there. And we'll talk a little bit more about that in just a minute. Okay, so here's a question. Are the following shapes similar? So now remember in that last example, right, if you look back at that last example, we were told that they were similar, and then we found a side length. Here, we're given a bunch of side lengths, okay, as you're going to be able to tell, and we're going to ask, are they similar? Okay, so we've got A, B, C, and D, and then those side lengths are listed. So the question is, are they similar? So we've got this smaller piece here, this E, F, G, and H. This is 3, 6, 5, and 10/3. Okay, so what we're going to do is look at the proportion. So I would start with the bigger side. We're going to do the big shape, that's my big shape, over my small shape. And then we're going to start with maybe the largest side length. So what's the largest side length in B, the big shape? Looks like 15. So 15 over, what's the largest side over on the other side? Looks like 6. Yeah, right, 10/3. Yeah, that looks right. So we're going to say 15 over, no, I'm sorry, there's a 5 here. Sorry, 5 is the largest. Oh, I made a mistake here. You're going to have to excuse me. Change this to a 1. Okay, I saw this G here and I was thinking it was a 6. Okay, so 15, the largest side over the largest side here, that's a ratio of 3, okay? It should equal all the other ratios. So the second largest side is a 10, and the second largest side here is actually 10/3, because 10/3 is 3 1/3, okay? So 10/3. Actually, if I divide 10 divided by 10/3, I flip and multiply, I actually get 3 again. So far we're looking good, right? We should be getting 3 as this common ratio here. Then I look at my second smallest side, so 9 over 3. That is going to be also 3. And then finally, my small side, 3 over 1. So as you can tell, all of these ratios are equal. That means it's proportional. So because it's proportional, then I say, yes, these two shapes are similar to each other. Okay? And again, this number 3 is my scale factor. It's saying it's 3 times as big. If I look at the sides, they're all 3 times as big. Every side times 3 makes the larger one. So that's my scale factor. Okay, so just kind of be thinking about scale factor. Sometimes it's good. All right, so here's an example of how you can use scale factor to your advantage here. Okay, so here's an example of a triangle with side length 6, 7, and 8. And I'm being told that it is similar to a triangle with lengths unknown, 16, and 14. Okay, all right, so I'm looking at this thing and I'm trying to see maybe what the scale factor is. I see that there's a 7, right? And then I see there's a 14. You see how that's twice? That's 2 times as big? I see there's an 8 and that it's 2 times as big. That means my 6 must be 2 times as big. So that must mean that x is 12. Okay? Works either way. You could start with the bigger numbers and notice that they're all half as big, so it would have to be 12 to make half as big be 6. But that's using scale factor to your advantage, okay? Now, scale factor and these kind of problems, they come into play a lot. So for some reason, they always use an example of a building or a tree or something with a shadow. So when you see these shadow problems, we're going to be using this idea of setting up this proportion. If we have a shadow problem, you've got a big building that has a shadow and you're, 6 feet tall and you have a shadow. Well, it's similar because it makes a triangle with equal angles, okay? And because we have similar triangles, then I can set up proportion problems. So the height of the building, right, over the height of the person should equal the shadow of the building over the shadow of the person. Then, of course, you just cross multiply those to solve. So that's the idea, is that shadow problems use this same idea. Also, you'll see it with, of course, similar figure problems like we've been seeing when you're told that these two shapes are similar. Okay, and then also you'll see it in scale drawings. So they'll say this drawing is to scale. So when you see scale drawings, the same thing applies. Like, there's a map that represents the actual city, and the scale is 1 to 316. 1 inch is 316 miles. So what you would do is realize that's the scale factor is, makes it 1 to 316. So you just multiply everything by 316 to get the miles. Okay, so those are the kind of times that you'll see problems like that, and that's pretty common on the ACT. I bet you'd see problems like that on every test you take. Okay, so you can think of these similar figures, okay, you can think these similarity problems like dilations. Okay, so from geometry, we talk about, a shape is being dilated. It means, it's whatever this is. If this is 2 and 3 and 4, this becomes 20 and 30 and 40. It's a dilation. So it's an expansion. So they work very, very similar. Okay, and again, that uses that scale factor of 10 in that dilation. Okay. So ratio of sides. So this is a similarity idea, but it's kind of a weird interpretation of it. But it's something I've seen on a lot of practice sets, so I want to make sure you go over it. So the ratio of side lengths. So let's say we've got two similar figures, maybe this rhombus here and this bigger rhombus here. Okay, and let's say this is 3 to 5. Okay, so you would say the ratio of the two sides would be 3 to 5, right? Ratio of the two sides. So the ratio of the area, this is kind of strange, but area is two-dimensional. It actually ends up being 3 squared to 5 squared. So they could ask you what's the ratio of the areas, and some people would have to calculate the area and then calculate the area and realize that it's this area to this area. But if you know what you're doing, you can say, well, it's two-dimensional. It's going to be 9 to 25. So if the ratio of the sides is 3 to 5, the ratio of the area will be 9 to 25. It's just 3 squared to 5 squared, okay? So what would the ratio of the volumes be? Let's say now this is maybe like a parallelogram cube or something, right? We've got some kind of thing here. Well, it's 3 cubed to 5 cubed. That's the ratio of the volume. So 27 to 125. That would be the ratio of the volumes. So basically the ratio of the sides is x to y. If the ratio is x to y, the ratios of the area is going to be x squared to y squared. The ratio of the volumes will be x cubed to y cubed. Okay, that's pretty standard. And so those problems are super duper shortcuts if you see something like that. So let's look at an example. Okay, so you've got a square with side length 5. So the sides are equal to 5 inches, okay? What's the ratio? Oh, sorry, you've got another square where the sides are equal to 7, okay? So what's the ratio of their side lengths? Well, that's easy, right? You just write the ratio as 5 to 7. Now remember, you could see it written as 5 over 7. 5 to 7, right? What would the ratio of their areas be? That would be 5 squared to 7 squared, so 25 to 49. Now let's say they're cubes instead of just squares, okay? So what's the ratio of their volume? Well, volume's three-dimensional. 5 cubed to 7 cubed, you get 125 to 243. I don't think I did that right. Sorry, 7 cubed is going to be 343. That's what it is. Okay, so 125 to 343. That's the ratio of those volumes. Remember, you could work this out by hand. You could say, okay, if you've got a cube here with side length 5, the volume is going to be 5 length times width times height. Well, that just gives you 125. And then the other one, right, is your 777. You're going to get 7 times 7 times 7 length times width times height, which is 343. So you're going to get still that area. But if it was a more complicated thing like a cylinder or something, and it starts getting real messy, that's a really good way to do it. So, all right, that's all I got for you today. Appreciate you guys being here, and we will see you next week.